Ali and Shaima, are you able to hear?
Yes, ma'am.
Okay. So in the last class, we had started with the adiabatic process. Isothermal we have completed, and we just started with the adiabatic process. So a very little portion is left. One, just the derivation of the work done during adiabatic expansion is left. And 2 to 3 numericals we also have to practice from this. So let us start with it. What was the adiabatic process? Whenever we say the term adiabatic, it means the heat cannot enter or leave the system. Okay, so no heat enters or leaves the system during adiabatic process. So I told you three formula also. PV to the power gamma is constant. TV to the power gamma minus 1 is constant. T to the power 1 minus gamma. T to the power gamma is constant. So these are the three formula that I told you. And I also told you that the value of gamma, which is the ratio of Cp by Cv, that also you have to remember for the monoatomic, diatomic, and triatomic gases. Now, work done during the adiabatic expansion. If you remember, this was the formula 2.303 nRT log V2 by V1 or P1 by P2 for the work done during isothermal processes. So for the isobaric process where the pressure is constant, work done is simply P delta. And one more thing, class, if there is isochoric process, means volume is constant. So if volume is constant, there is no change in work done. There is no change in volume. Delta V is 0, so work done will also be 0. So that's why work done, we saw no 4 processes. These 4 processes we saw. So in isothermal process, we saw the formula of work done as 2.303 getting multiplied. Isobaric, pressure is constant. The formula will be pressure into change in volume, where pressure is constant. If pressure is variable, we use the integral formula. So but for isobaric, this is the formula, not the integral one, because pressure is constant here. Isochoric, volume is constant. There is no change in the volume because volume is constant. Initial and final both are same. So here work done becomes 0. And adiabatic is left, which we are discussing. So all the 4 processes are there in your syllabus. It's just that one of them we have already done. In another, it is simply 0. So yeah, this is a question which is based upon this. An ideal, this we saw in the last class. This question was left, right? We just completed it till here. Or this also we did 3 by 2. No, we have completed this. Yeah, this question we have seen. You have to start with the work done during the adiabatic process. So I'll start with the variable work done first. Whenever you have the work done during the adiabatic process, so work done is what? It is P d. So work done is P dV. So we are integrating from V1 to V2. This is the formula of work done. Now, since we are using adiabatic process, we know PV to the power gamma is what? It is constant. So instead of constant, I cannot write constant all the time. So what I'll do, I'll just put a K. PV to the power gamma is K. That is constant. So what is pressure from here? Pressure will be K divided by V to the power gamma, right? Now see, if I put the value of pressure here, because the problem is that pressure and dV, they cannot be integrated together. They can neither be differentiated or nor integrated, because you have to have the same variables for the differentiation or integration to occur. This I have told you in your, repeatedly I have told you first thing. Secondly, we have discussed this in the calculus part. Now, coming to the work done. When we are talking about the work done, so work done is equal to, if I put the formula of pressure, it is K V to the power gamma dV, integrating it from V1 to V2. This is the formula of it. Like not the formula, basically if you just substitute pressure here. Right? Now class, when something is there in the denominator and you have to bring it up to the numerator, what will happen? The sign will change. So work done will be written as K V to the power minus gamma dV from V1 to V2. From V1 to V2. So here work done is equal to K. Now look, let us integrate. So how do we integrate? We add +1 to the power, and whatever is the power, we divide it in the denominator, and then we put the limits from V1 to V2. Now we are going to put in the limit, substitution of limits. So what will the work done be equal to? K by, what is this? 1 minus gamma. K by 1 minus gamma is already the constant term. Let us substitute the limits now. Look, instead of V, we have to put the upper limit first. So instead of this V, I am putting V2 first. So it will be V2 1 minus gamma minus V1 to the power 1 minus gamma. Minus gamma plus 1 or 1 minus gamma. Both are the same. So this is what I have put. Now, let us do one thing. Let us multiply this K within the bracket so that we can write down the numerator. So work done is equal to, this will be K times V2 to the power 1 minus gamma minus K times V1 to the power 1 minus gamma divided by 1 minus gamma, right? So see one more thing, class. Here, from here, PV to the power gamma, when it is constant, what does it mean? It means P1 V1 to the power gamma is equal to P2 V2 to the power gamma. This is constant, right? So what I can do, I can put the value of constant like this. Look, instead of this constant, because this constant is nothing. This constant is nothing. This is, that's why we are replacing it. So we are replacing it with P1 V1, then here V2 to the power 1 minus, okay, we'll put all the like terms together. This is 2. So P2 V2 will be put here. Minus again P1 V1 into V1 to the power 1 minus gamma divided by 1 minus gamma. Now let us just simplify it a bit further. P2 V2 into V2 1 minus gamma is there, right? This, so simply what can we do? One more thing, class. You remember the ideal equation which I told you? PV is equal to nRT. So from here, P1 V1 can be written as nRT1, and P2 V2 can be written as nRT2. So your work done here can be written as, see, firstly, one formula of work done will be P2 V2 minus P1 V1 divided by 1 minus gamma. Okay. P1 V1, sorry, P2 V2 minus P1 V1 divided by 1 minus gamma. Okay. Why? See here. This is P2 V2 to the power gamma 1 minus gamma. This P1 V1 to the power gamma into V1 1 minus gamma. So when the bases are same, powers get added up. So gamma gamma gets cancelled, right? So here gamma gamma will be cancelled. So formula will be P2 V2 minus P1 V1 by 1 minus gamma. Or when we put this, when we substitute P1 P2 P1 V1 P2 V2 from here, one more formula which you can use is nRT2 minus nRT1 by 1 minus gamma, which you can further simplify and write as nr can be taken common, T2 minus T1 by 1 minus gamma. So this is one formula which you can use. This one, if you have pressure and volume, and if temperature is mentioned, then you can use this. Tell me, class, have you understood this derivation?
Yes, sir.
Okay, I'll just repeat very shortly in a quick manner. If anyone has any doubt, you can ask. Variable pressure is PdV. We know PV to the power gamma is constant. So we just put a K and calculate the value of P, that is K by V to the power gamma. We put it in this formula, and then we bring V to the power gamma up so that we can integrate it. We have integrated it here. Minus gamma plus 1 will be there. Minus gamma plus 1 will be there. Then what we are doing? We are taking the constant term out. And then we are putting the limits because we are integrating it. Now, this is what we did. We multiplied k into the brackets. Now we have this. P1 V1 to the power gamma, P2 V2 to the power gamma is the constant. So now we are replacing this value back. Gamma 1 minus gamma, bases are same, powers get added up. So gamma gamma gets cancelled. Ultimately, we have the formula P2 V2 minus P1 V1 by 1 minus gamma. From the equation PV is equal to nRT, we are calculating this value. Okay. So please write it, then we'll begin with the numericals. 1 or 2 numericals is there. This chapter is almost over. So it's a very important chapter and a very easy chapter. So please practice class well. And after this, I'll start with kinetic theory. Then your waves and SHM will be left for the Jan. And whoever is getting the dates of exam, please let me know. Okay. So I hope till here this chapter is clear. Zainab, is it clear? Zainab,
Yes, ma'am.
Shaima, clear to you? The entire chapter?
Yes, ma'am.
Jesleen, fine. Ali Mohammed? Okay, okay, okay. Please write class. Done.
No, ma'am.
No, Shaima, that gamma is different, the coefficient of cubical expansion. This gamma is Cp by Cv. I told you, I think, when we were discussing the specific heat capacities ratio in thermal properties. That time we discussed. So this is ratio of Cp by Cv. This is the constant gamma. That is also, see, the alpha, beta, gamma, all these simple symbols get repeated a lot because these are very common Greek symbols that are there. So that's why, but this is the different gamma. This is not the cubical expansion one. So don't relate it with that. Cubical is separate and this is separate. This is Cp over Cv, specific heat at constant pressure and constant volume. Okay. Now let's solve this question. This says that 1 gram molecule of an ideal gas at STP is subjected to a reversible adiabatic expansion to double its volume. Now, see the relationship between the volume. Volume is getting doubled. Find the change in internal energy in the process. Now, look at this question when you have to find out the change in internal energy in the process. Look, how can we relate these things? For change in internal energy, you need the work done. Look, class. See, if you get these kinds of questions, how to proceed in the exam? It is saying, first see which kind of process it is. Yes, it is saying, yeah, it is adiabatic process. So with adiabatic, it should immediately come to your mind that work done will be equal to the entire energy. See, according to the first law of energy, work done plus change in the heat is equal to the change in internal energy. In adiabatic process, there is no exchange of heat. So this will be 0. So entire work done will be equal to change in internal energy. So basically the question is asking you to calculate work done in the adiabatic process. That will be equal to internal energy only. So instead of directly asking you the work done, it is asking you in this manner. So proceed the questions this way. And see, work done during adiabatic expansion, we know the formula, we have just derived it. So firstly, let's see the relation. Let's find out the temperatures, because one temperature is given, volumes values are not mentioned, so we cannot use the formula P1 V1, right? P2 V2 minus P1 V1. Where is the pressure? Where is the volume? With volume it being its double, we need one volume at least. We don't need the volume, we need the volume and the pressure, but we don't have any information. But at least we have one temperature, we can calculate the next temperature. So temperature T1 is there, T2 is missing, but volumes relation are also there. So let's proceed with the temperature. T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. What is the first temperature? 273. What is the first volume? This is simply V to the power gamma minus 1. What is gamma? 1.5. So what is 1.5 minus 5? 0.5, right? So this is 1.5 minus 5. T2 we don't know. V2 it's doubled. So 2V to the power 1.5 minus 1. Correct. Now look, 1.5 minus 1 is simply 0.5. That is half. And half is what? Ma'am, suppose the volume is given and pressure isn't, can we take pressure as atmospheric pressure? No, unless it is mentioned. And if volume is, both the volumes are given and one of the pressure is given, okay? Or if you have no information about the temperature, like here there was information about the temperature, then only you can take the pressure at atmospheric, because unless, one more thing, STP has to be mentioned. Otherwise, there must be some other thing in the question. If you see STP is there and there is no relation between temperature, some relationship between volume is given, but you have no clue about the temperature, then directly go to the pressure, what you are saying, Shama. That is then correct. But provided STP should be mentioned. Now, this will be, this is 2V. So if we are calculating T2, see, this V and this V part will be gone, and 0.5 is half. 2 to the power half means root 2. So T2 will be 273 by 2 to the power half, or root 2. So if we put this value, 273, this would be, if we put all this value here, 273 divided by 1.41, because of the values of root 2. So T2 will be 273 divided by 1.414 something. So the answer will be equal to, almost it is equal to 193 Kelvin. This somebody check and confirm also what is this value, exact value. Now we have T1 and T2. We can simply use the formula NR T2 minus T1 divided by 1 minus gamma. So if we put in the values here, class, what should it be? Work done will be, now you can put the values. This will be equal to the change in internal energy. Work done will be, this is 8.314. T2 minus T1, 273 minus 193 Kelvin. Here, don't don't take it as negative. Like even if you're taking 193 minus 273, take the mod if your temperature 2 is bigger or smaller. So that's I'm directly writing 273 minus 193. Take the mod here. Okay, greater minus the lesser one. Then this is 1 minus 1.5. What is 1 minus 1.5? Again, this, okay, the here, now see, from here automatically your negative will come. Whatever was the negative, na, here automatically it will come. And you will also see your answer getting negative directly. So this will be, work done will be 8.314 into 80 by minus 0.5. Or let's put it, because it's T1 is mentioned in the question. If it was not mentioned, we wouldn't have taken. Let's take it as negative because it is mentioned in the question T1. we cannot change, because T1 has clearly, if temperature is directly just given, you can, because in work done we have to keep the sign conventions in mind. So it will be 193 minus 273 only. Okay, because the first temperature has clearly been mentioned as T1. Now we cannot change it. So this will be also minus 80. Then we will see whatever answer is coming. So this minus will be cancelled. 2 will go up. 160 would be there, right? So this would be work done will be almost, the answer to this is given as 1330.24 joules. So precise answer you can check. Okay, this will be plus. Okay. So because the negative sign has gone, this is work done will be plus. Now let's see the formula of it. Delta Q is 0 in which process? It is 0 in the adiabatic process. Right? What is the first law? First law will be the change in the, change in the heat is the sum of change in internal energy plus the work done. The Q is 0. So that's what was the question saying, calculate the work done. So work done here will be the negative of change in internal energy. So your internal energy will have the same value, just put in minus sign, 24 joules. All right, this is how you have to solve the question. 1 or 2 questions we'll see for the practice from the first law of thermodynamics. First law of thermodynamics will be getting connected. Oh, here I have written the opposite. It will be minus here. Okay, so this will be delta U plus work done is the change in heat. All right, please write it. Yes, who is this? Afnan Adil? Okay, class. So this question gives us a graph in figure. The changes in the states are mentioned. So A to B, B to C. Okay. And one is by AC. So two paths are there, A, B, C, and one is this AC path. So this says find path along which the work done is the least. So see what we can do along which path the work done is the least. So this is there, we can see from here, this is the displacement that is there. So a work done according to AC will be shorter. Why? Because work done, we see the area under the graph. Now for ABC, this entire will be the area, right? This is saying a shorter area or the longer one? Least, yeah. So this entire one will be for the ABC. But for just the AC part, this will be the work done. So work done under the area, area under the graph, this will be least. So it is asking find the path. And so work done also you can calculate. See, work done along AC, if you are calculating, that is simply 15 into 4, which will give you 60 joules, right? And if you are calculating the work done for the entire ABC, that will be half sum of the parallel sides. One is 5 and other is 15, right? And what was the base? Yeah, this was the 4, the height. So that will be 20, 10, 40 joules. So this is still this work. ABC is coming more by calculations. Okay, this is AC. Trapezius one is AC. Okay, I've written the opposite. Yeah. Trapezius one is the bigger one. Yeah. So work done is least in that. By calculations also it will come. Now see, for ABC, it will be the entire, for AC, it would be just this trapezius, and this would be the rectangular part. So rectangular part, that is ABC, it is coming 60 and just AC. So work done is the least in AC. By the graph also, you can also see. Here it just said fine. So if it's 1 marker, you can simply write this. If it is 2 marker, you have to show. Second part says internal energy of a gas at A is 10 joules. Amount of heat supplied, okay, is to its state to C through AC is 200 joules. And you have to calculate delta U at C. See, delta U at A is given as 10 joules. Okay. A to C it is asking. Delta QAC is equal to delta U of AC plus work done of AC. Work done of AC, we've already calculated 40. So see, this will be 200. Now, look, this is 40, right? So this will be delta U is there. So delta U will be 160, right? Delta U will be 160. Now, we have to find out the change. This was given 10, so 170 will it be? See, UC minus UA is calculated as 160. UC we have to calculate, this is 10, so 10 will be added here. So UC will be 170 joules. Right, and lastly it is saying internal energy of a gas at state B is 20. Same thing, but you have to calculate now the heat supplied to it. So it is even shorter than the previous one. The third part says, see, UA is given as 10 joules. UB is given as 20 joules. So this time these two things are mentioned. What else? Internal energy is of a gas at state B is 20. Find amount of heat supplied from A to B. Okay, look class, A to B. Can anyone tell me, is that what is the change in volume from A to B? For the work done, we need volume. Can anyone of you tell me what is
Zero.
it? Yes, Shaima?
0.
0. Correct. It is 2. It is constant. Yes, Rena Benali. Right. This is 0. So 0. So work done. There is no need of work done because volume is constant. That's why we have this graph also. So UB is 20. Work done in A to B is 0. What is delta Q? This is basically the question. Delta Q is equal to delta U plus delta W. Delta Q will be change in work done, that is 20 minus 10. This is 0. So delta Q will be 10 joules. So do you see the questions are just formula based, but you need to apply lots of things, whatever you studied. Tell me, class, this question is clear to all?
Yes, ma'am.
Yes.
Okay, write down the solution. One last question is there. That's a very easy one, but it is important. Let us complete that also. Please write this very quickly, class.
Ma'am, can you show the third part of the question?
This part?
Yes, ma'am. Done, ma'am.
Okay, class, just the last question for today and for this chapter. This says that a 0.5 mole of gas at temperature 300 Kelvin. Okay, 0.5 moles are given. Temperature is 300 and it is expanding isothermally from an initial volume of 2 liters to 6 liters. It is saying what is the work done by the gas, estimate the heat added. See, work done by the system, work done on the system. Heat added, heat emitted. You have to be very careful because the sign conventions will change your answer. And lastly, it is saying, see, R's value is given 8.31. So what is the final pressure? So it's an easy question, but these kinds of questions only will be there in your exam. But at once, if you do not study and just look at the question, you'll not be able to relate. See, first part, what is the work done? So work done will be nRT log V2 by V1. That's what we do because here it is volume given. So number of moles 0.5. R is 8.31. 4 also we will not put, it is given 8.31. Temperature is given as 300 log V2 by V1, 6 by 2. Okay. So this is equal to 1.369 kilojoules. This you can solve and check. Even I have not solved it right now. The answer I just remembered. So please cross check when you are writing. Second part says, see, isothermal. Isothermal means change in temperature is 0, right? Internal energy will be 0. Remember, isothermal this, adiabatic में delta Q 0 होगा. Isothermal में delta U 0 होगा. You have to remember this. Now, according to the first law, delta Q will be equal to work done. Delta Q will be, what is the work done? We have already calculated 1.369 kilojoules. So that's why first part has to be right. Otherwise, you will be copying the wrong value. Last part is saying final pressure. So very easy. This one is very easy. See, this will be simply P is equal to nRT by V. Whatever is the final volume, because we are calculating the final pressure. Okay. So this will be 0.5 into 8.31 into 300. Final volume is 6, right? But it is not in the SI unit, no? 6 into 10 to the power minus 3. So this final value will be 207.75 kilopascals. So again, please check the values. This and this, both of it. Okay, so this is how you have to relate all the concepts of what you've studied of thermodynamics. Quickly write down it and class update me in the chat column. This completes the thermodynamics chapter. Now we'll meet on Saturday and we'll complete the kinetic theory.